Hey everybody, this is example number 6 for structural dynamics covering the response to harmonic excitation. And the problem statement that we have is the rotating machine shown in the figure below has a total weight of 500 pounds. And when the operating speed reaches 2,000 revolutions per minute, the machine exhibits an unbalancing force of 5 pounds at an eccentricity of 5 inches. Resonance was seen to occur at an operating speed of 1,000 RPMs, and the damping factor is estimated to be 0.001. So we need to find the vibration amplitude for the system at 2,000 RPM, and also find the stationary value of the steady state vibration amplitude if the operating speed is very high. So here's our figure of our representative model of our rotating machine, and it's mounted to some foundation maybe which has some stiffness, K/2, and it has some damping effects. And at a certain operating speed, it has an unbalanced mass here shown, and the unbalanced mass is acting at an eccentricity E. And so we need to calculate the amplitude of the vibration amplitude for the system, the steady state vibration amplitude at 2,000 RPMs, and also we need to calculate the steady state vibration amplitude when the operating speed is very high, so it's much greater than 2,000 revolutions per minute. Before we proceed with the solution, I just want to let you guys know that this example is brought to you by Bentley. And Bentley Systems is a software development company that supports the professional needs of engineers, designers, planners, and contractors responsible for creating and managing infrastructure. Bentley has tailored software applications for design, modeling, and analysis of buildings, structures, bridges, plants, and more. I have used Bentley's software, and I can say that the software was very easy to use and the support that came with it was impeccable. Whenever I needed help, the Bentley team was there for me. And here's their website, it's bentley.com. There's a link to bentley.com and some of their YouTube channels within the description part of this video. So if you're a student and want to get familiar with the software and get a leg up over your colleagues during your job search, academic licensing is available through Bentley. And if you're a practicing engineer and you want to just sharpen up your skills, they have a bunch of videos and webinars on their website as well as their various YouTube channels, so please check them out. And now coming back to our dynamics problem, the first thing we're going to do is calculate the circular natural frequency of the system. And we know, we were told in the problem that resonance occurred when the operating speed was 1,000 RPMs. So that tells us that's the value we're interested. So we convert the 1,000 RPMs into radians per second by multiplying by 2 pi, and 2 pi divided by 60. So the circular natural frequency of the system is equal to 104.72. Next, we're going to do the same thing with the operating frequency. Convert it from revolutions per minute to radians per second. And so the operating frequency, 2,000 revolutions per minute, multiplied by 2 pi divided by 60. So it's equal to 209.44 radians per second. After this, we can calculate the frequency ratio, and that's equal to the excitation frequency, the operating frequency you can say, divided by the natural frequency of the system. So 209.44 divided by 104.72, so that's 2. R equals 2, the frequency ratio. And now we can calculate the steady state amplitude. And this is a formula for the steady state amplitude when you have some type of rotating unbalance. And so the formula is equal to the mass of the unbalanced mass, small m, times eccentricity E divided by the total mass of the system times r squared divided by the square root of 1 minus r squared plus 2 times zeta times r squared. And zeta is a damping factor. And so now we can just plug in the values into this formula and find the steady state amplitude. And here, the only thing to note here is that instead of plugging values for the actual mass, what I've done is I just input the value for the weight. So the weight, small w, we can say, and big W, because mass is equal to weight divided by gravity. And so basically what I'm saying is that this gravitational, the G, would just cancel out here. So instead of using small m divided by m, we can just do small w divided by capital W, the weight of this unbalanced mass divided by the total weight. And then the eccentricity is 5 inches, and then r squared is, and the r is 2 squared divided by the square root of 1 minus 2 squared plus 2 times 0.001 times 2, and this is squared. And then the bottom denominator, you take the square root of that. So the steady state amplitude at the operating speed that we have of 2,000 revolutions per minute is equal to 0.0667 inches. And lastly, the problem statement asks us, what happens when what's the steady state vibration amplitude when we have a very large operating speed, when the excitation frequency is going very large? So here's just the basic formula for our steady state vibration amplitude, which we already introduced in the previous step. So what happens is, if you plug it into some spreadsheet, you'll see that as you increase the operating frequency omega, as that goes larger and larger, this part of the formula, it just approaches 1 here. So what we can say is that as operating frequency increases, the vibration amplitude will converge to this value of small m times E divided by capital M's, or you can say small weight, the unbalanced weight times eccentricity divided by the total weight, and that is equal to 0.05 inches. And this is the end of this example. Please subscribe to the channel, like the Facebook page. It's facebook.com/engineeringexamples. And please also visit our website at EngineeringExamples.net. Thanks.